It's a really fascinating paradox in the modern business world right now.
Oh, absolutely.
Because if you walk into, well, pretty much any major tech company or frankly any enterprise today, and you sit down and pull up an executive dashboard.
Right, the high-level metrics.
Exactly. On that dashboard, everything looks like a perfectly oiled machine, you know?
Completely.
Yeah.
The charts are green. The cloud costs are all neatly categorized into these beautiful little pie charts.
Right. And all the optimization metrics are just ticking upward. It all looks so incredibly visible and controlled.
But then you take the elevator down, right? You go down to the engineering floor.
Yeah, and you sit with the actual platform operators.
And you realize very quickly that you're looking at two completely different realities.
It's just night and day. On the ground, it's this raw, unvarnished gridlock. I mean, we're talking about frantic multi-region deployments, midnight auto-scaling failures, and engineers who are basically drowning in configuration files just to keep the lights on.
It's the absolute definition of a structural illusion, really.
A structural illusion. I like that.
Well, it is, because we've built these massive, sprawling digital infrastructures over the last, decade or so, and we measure their success by these highly sanitized, high-level financial metrics.
Right, the stuff that looks good in a quarterly report.
Exactly. But beneath the surface, there's this massive hidden friction.
Yeah.
It's the friction of data physically traveling too far, of systems just sitting around waiting for things to happen, and of human beings essentially acting as the duct tape, holding a fundamentally fragmented architecture together.
And that's exactly what we're unpacking today. We're going on a deep dive into the hidden trillions, literally trillions, that get lost in these bloated, centralized cloud architectures.
And more importantly, we're looking at how to actually fix it.
Exactly. We're going to explore how adopting a minimalist, design-first mindset can drastically reduce your costs, kill your latency, and honestly, just stop your engineering teams from completely burning out.
It's such a vital mission for our deep dive today. Our goal is to help you, the listener, spot these invisible structural bottlenecks in your own org.
Things that don't always show up clearly on the bill.
Right, things like compounding egress fees and fragmented vendor stacks that are just quietly draining your organization's resources. And we have some really incredible source material to guide us through this.
We really do. First up, we're pulling from a super fascinating strategic operations manifesto by the elite deep tech analyst Prasad Bond.
It's a great piece. It's called The Quiet Architect.
Yeah, and it outlines concepts like the trillion-dollar blind spot and restorative engineering, which we will definitely get into. And we're pairing that with a highly technical breakdown from Matt Butcher at Akamai.
Right, his piece titled, Your Origin Server Might Be Your Most Expensive Decision.
So let's just set the stage here with a bit of a mental model, because we're going to be talking a lot about architecture and design today.
Always good to have an anchor for this stuff.
So have you ever looked at a vintage Braun radio? Or, maybe even like an early iPod?
Oh yeah, beautiful industrial design.
Exactly. They're famous for following the design philosophy of the legendary industrial designer Dieter Rams.
Right, the whole less but better ethos.
That's the one. Functional clarity, visual order, reduction. He basically believed that good design was all about stripping away every single unnecessary button, every superfluous dial, until you were left with something that was just perfectly intuitively functional.
And what makes our sources today so compelling is that they're essentially demanding we take that exact physical design philosophy, Ram's philosophy, and apply it to our invisible cloud architecture.
Which is such a cool concept. Just as Ram stripped away the unnecessary buttons from a radio to make it better, our mission today is about stripping away every unnecessary network hop.
Every redundant centralized server check.
Yes, and every fragmented vendor seam. The goal is to make your internet applications function the way they were always supposed to function. Clean, fast, and incredibly cost-effective.
Which naturally leads us right into our first major concept from Prasad Bond's manifesto, the trillion-dollar blind spot.
Let's get into it. What exactly is this blind spot?
Well, Bond points out something really interesting about modern professional discourse right now. If you spend time on platforms like LinkedIn or X, you'll notice this profound shift in how engineers are communicating.
How so? Like, less corporate speak.
Exactly. We're moving away from that sanitized corporate PR. Instead, frontline professionals and engineers are sharing these raw, authentic accounts of systemic failures.
Oh, like those viral postmortems you see popping up all the time?
Right, exactly. They're posting detailed postmortems about their operational gridlocks and these million-dollar architecture mistakes they've made.
But they aren't just complaining for the sake of complaining, right?
No, not at all. They're validating this invisible, completely undocumented labor that it takes just to keep these massive centralized systems from collapsing in on themselves.
It's like the duck paddling furiously underwater while looking calm on the surface.
Such a good analogy, yeah.
Yeah.
Bond argues that these viral discussions aren't just isolated hiccups. They're actually exposing a pattern of structural design flaws that are deeply embedded in how we build things today.
And the blind spot really manifests in what he calls the capacity overhead and centralized cloud trap, right?
Yeah, think about how a typical enterprise handles a bloated cloud bill. The CFO starts complaining, so they bring in an external consultant or they dedicate a whole quarter to a massive cloud optimization sprint.
The classic cost-cutting sprint, everyone's favorite time of year.
Oh, it's brutal. So the engineering team goes in, they right-size the computing instances, meaning, they downgrade a server with 64 cores to 32 cores just because it wasn't being fully utilized.
They kill off some zombie resources that someone spun up for a test and forgot to turn off.
Exactly. And maybe they renegotiate their reserve capacity contracts with their cloud provider, and at the end of the quarter, magically the cloud bill goes down by 15%.
And the executives pop the champagne, the dashboard is green again.
But, and this is the crucial part, Bond and Butcher both argue that this entire exercise is a total illusion.
An illusion. How so? Saving 15% is real money.
It is real money, but you're celebrating a 15% reduction while completely missing the architectural design flaws that are the actual fundamental budget drains. You're basically optimizing a broken system rather than questioning the design of the system itself.
Okay, but if they're saving 15%, isn't that still a net positive? I mean, for you listening right now, why is the industry so hyper-focused on tweaking server sizes if looking at the actual blueprint of the architecture yields better results? It feels like there's a disconnect there.
There's a massive disconnect, and it comes back to what Dieter Rams would call a lack of honest design.
Honest design. Break that down for us.
A cloud architecture is not honest if it looks efficient on an executive spreadsheet, but it requires massive undocumented human labor just to keep it from falling over.
Oh, I see.
The reason the industry focuses on server sizes is because server sizes are highly visible. They have a clear line item on the monthly bill. It's very easy to look at a spreadsheet and say, we were paying for an extra large instance, now we are paying for a medium. Look at the thousands of dollars in savings.
Right, it's tangible. A non-technical manager can understand that.
Exactly. But the true architectural bottlenecks, the things draining the real money, they're obscured. They're hidden by geographical silos. They're embedded in legacy code from 5 years ago. And most importantly, they are split across completely different departmental budgets.
Ah, so no single person actually sees the whole picture of the waste.
That is the absolute crux of it. Think about it. If the network team pays for egress bandwidth, and the application team pays for the core compute servers, and the security team pays for bot management.
Nobody is looking at the holistic design.
Right. They're all just trying to optimize their little slice of a highly bloated pie.
Which is just wild when you step back and look at it.
It is.
Yeah.
Bond notes that to fix this, we really have to bypass our own egos. We have to normalize these operational failures as a shared industry struggle. It's not about pointing fingers at the engineers who built the system 5 years ago.
No, because they built it with the tools and mindset of that time.
Exactly. It's about recognizing that the standard centralized cloud model is just inherently flawed when it comes to modern global scale.
Because tweaking those centralized servers only yields superficial savings. To get the real savings, the source material tells us we have to examine the architectural core itself, and that brings us to the engine of this entire bloated system. The origin server.
Yes, the origin server.
Let's unpack the physics of this, because this is where Butcher's piece from Akamai gets incredibly specific. We're talking about the origin server trap and the punishing cost of the round trip.
This is where things get really tangible. The fundamental flaw here is routing way too many high-frequency, lightweight decisions all the way back to a centralized origin server.
And to really grasp this, we need to think about the physical reality of the internet, right?
Oh, totally. We use the word cloud so much that we forget the internet is not a magic cloud.
Right, it's physical.
It's highly physical. It's a series of fiber optic cables, massive routers, and physical data centers sitting on concrete slabs. Now, think about the basic interactions a user has with an application today.
Okay, like a bot classification check when they first connect?
Yeah, or a simple URL redirect,
Mm-hmm.
or even just fetching a personalized greeting payload like, "Welcome back, John."
Pretty standard lightweight stuff. It shouldn't be hard.
It shouldn't be.
Yeah.
But in a traditional centralized architecture, every single one of those tiny interactions requires a data packet to physically travel from the user's device, let's say they're in London, all the way across the ocean via submarine cables to a centralized cloud region.
Like a massive AWS data center in Virginia.
Right. It has to travel to Virginia, process the logic, and then physically travel all the way back to London.
And every single time that happens, there's a literal toll booth on the highway. We're talking about egress fees.
The most visible penalty of the origin server trap, egress fees. Anytime data leaves a cloud provider's network to go back to the public internet, they charge you an egress fee.
To get you coming and going.
Well, mostly going. But the disparity in these costs is staggering when you look at the raw data. According to the Akamai source, if you're routing this data out of the major centralized hyperscalers,
Yeah.
you are paying a massive premium.
Let's put some numbers to that for the listener.
Sure. AWS charges roughly 9 cents per gigabyte for egress. Google Cloud Platform is even higher, around 12 cents per gigabyte. Azure is sitting at around 8.7 cents.
Wow. And I noticed in Butcher's article he mentions NAT gateway fees are stacked on top of that. Can we clarify what a NAT gateway actually is in this context? Because that sounds like just another sneaky tax.
It basically is. A NAT gateway, or Network Address Translation Gateway, is essentially a necessary evil in centralized cloud networks. Your application servers usually sit in a private network for security reasons, right?
Right. You don't want them exposed directly to the public web.
Exactly. They don't have public internet addresses. So when they need to send data back to a user, that data has to pass through the NAT gateway, which translates the private address into a public one.
Okay, makes sense.
But cloud providers charge you an hourly fee just to have the gateway running, plus a per gigabyte fee for the data passing through it.
Unbelievable.
So you're paying for the egress itself, and you're paying a toll to the gatekeeper just to reach the egress point.
It just compounds. It's a tax on top of a tax.
It really does compound.
Yeah.
Like, compare that 9 to 12 cents per gigabyte to a decentralized edge-native approach like Akamai Cloud, where the egress charge is just half a cent.
half a cent.
Yeah, $0.005 per gigabyte.
So 0.005, that's practically a rounding error compared to the big players.
It really is. But the hyperscaler fees are definitely not a rounding error. At an enterprise scale, the Gartner data cited in the Akamai piece shows these egress fees compound to make up 10 to 15% of a typical corporate cloud bill.
Just to move the data out.
Just for transit.
Hmm.
And if you're running a data-intensive workload, say video streaming or heavy API traffic, those egress fees can soar to 30 or even 40% of your entire cloud bill.
Okay, let's visualize this, because the concept of network routing can get abstract really fast. To explain the origin server versus edge computing, I like to look at the postal system.
That's a good way to frame it.
The origin server setup is basically like mandating that every single piece of mail in the United States must first go through one massive centralized sorting facility in Ohio.
Right.
Even if you're just mailing a letter to your next-door neighbor in California, that letter has to be put on a plane, flown to Ohio, sorted, and then flown all the way back. You're paying for the jet fuel, you're paying the pilots, and you're waiting days for a delivery that should have literally taken 10 seconds.
That captures the inefficiency of centralized cloud architecture perfectly.
Whereas edge computing, from what we're learning, is like putting a postal carrier on every single street corner. You hand them the letter, they look at it, see the address is right next door, and they just walk it over. No planes, no massive fuel costs, no waiting.
And if we connect this back to Dieter Rams's design philosophy, that centralized sorting facility in Ohio completely violates his core principle of reduction.
Right. Less but better.
Exactly. A design that requires maximum effort in this case, data traveling halfway across the globe for a minimum result, like a simple redirect, is just functionally flawed. Rams taught that good design makes a product useful and understandable.
And there is nothing useful about sending a simple authentication token 3,000 miles just to get a yes or no answer.
Precisely. It's the definition of bad design.
So we're forcing data to travel thousands of miles just to authenticate a user or load a basic profile. But while that data is making that massive round trip, the origin server isn't just processing, it's waiting.
Yes, it is.
It's sitting there idling while the data travels. Which brings up a huge question for our listeners. How much is that waiting actually costing us? Because we've all been sold this dream of cloud elasticity for years, right?
The auto-scaling dream.
Exactly. Auto-scaling. The idea that your infrastructure just magically expands and contracts based on exactly what you need at any given microsecond.
It's a beautiful concept on paper. The industry calls it just-in-time scale-up. But as Matt Butcher's piece highlights so well, the reality is much, much messier. And it exposes the massive hidden enterprise expense of idle cloud capacity.
So what's the rub? Why doesn't it work like the brochures say?
The problem with centralized auto-scaling is the physical latency inherent in spinning up new resources.
Why is it so slow, though? Like, what's actually happening under the hood when a cloud scales up?
Let's walk through the actual mechanics of it. When a massive spike in traffic hits, say, an influencer with 10 million followers posts a link to your e-commerce site, that traffic flood is instantaneous.
Right, it hits all at once.
Yes. Your load balancer starts screaming that they need more help. The autoscaler gets the signal and requests a new server from the cloud provider.
Sounds fast enough so far.
The API request is fast, sure, but the execution isn't. The cloud provider's hypervisor actually has to carve out virtual CPU and memory. Then it has to boot up a Linux operating system from scratch.
Okay, that takes a second.
Then once the OS is running, it has to pull down your massive application container image over the network. And those images can be huge. Then it has to unpack it, start the application, connect to your database, and pass a series of health checks before it's actually allowed to serve a single piece of user traffic.
Wow, and how long does that whole process usually take?
That entire sequence, it easily takes minutes.
And in internet time, a few minutes is an absolute eternity.
Exactly. By the time your autoscaler actually registers the spike, provisions the new servers, and gets them online and healthy, the viral moment might already be over.
Or worse.
Right, or worse, the initial flood of users just experienced a bunch of 502 bad gateway error pages, and they've completely abandoned their shopping carts. You've lost the revenue.
So because the underlying mechanism is literally too slow to react dynamically, companies are forced to pad their capacity artificially just to survive.
That's it exactly. It's the psychological comfort of over-provisioning versus the financial reality. Out of sheer terror of experiencing downtime during a critical moment like Black Friday, engineering teams will set their minimum server counts artificially high.
They're hoarding servers.
They are. They'll keep CPUs running at maybe 15 or 20% utilization, just so they have that buffer, that headroom ready to go.
You mentioned Kubernetes in the source notes regarding this idle waste. Can you unpack how Kubernetes plays into this for the listener? Because Kubernetes is supposed to be the ultimate optimizer, isn't it?
It is supposed to be. Kubernetes is basically an incredibly powerful orchestration system for managing containerized applications. It's the gold standard for deploying software today. But Kubernetes needs a baseline of worker nodes. Those are the underlying servers running constantly, so it actually has a place to schedule new application containers quickly when a spike hits.
So it still needs the physical headroom.
Exactly. The control plane needs a place to put things. Industry surveys on these Kubernetes clusters show that anywhere from 30% to 65% of paid-for cluster resources sit entirely idle.
Wait. Up to 65%?
Yes, entirely idle.
So we're essentially renting empty apartments in the most expensive city in the world just in case a dozen relatives show up unannounced for 5 minutes once a year.
That is the perfect analogy. You're paying maximum real estate prices for air, just empty space. And applying Dieter Ram's philosophy here again, this is the complete antithesis of functional clarity. The system is bloated with unused, heavy parts, strictly to compensate for its own architectural inability to react quickly. Good design is as little design as possible. But here we have massive, idle digital factories humming along 24/7, burning electricity and capital, simply because the centralized architecture is too rigid to be truly nimble.
It's wild when you step back and look at it. We're paying massive egress tolls for data to travel too far, and we're paying rent on servers that are literally doing nothing.
It's a tremendous amount of waste.
But, as Prasad Bhan points out in The Quiet Architect, the physical bloat of these idle servers directly leads to the next massive bottleneck. And honestly, I think this might be the most damaging one of all.
The human cost.
Yes. The intense human labor required to manage all of this unnecessary complexity.
We really have to talk about the human cost. Bond defines this through the lens of what he calls restorative engineering.
Restorative engineering. Tell me more about that.
His core mandate is that technology must restore human safety, capability, and dignity.
Dignity. That's a strong word for IT architecture.
It is, but it's accurate. When you force brilliant engineers to spend their days managing the bloat and the endless configurations of a centralized cloud, you're actively degrading their capability. You're stripping away their dignity as creators.
Yeah, that makes sense.
The Akamai piece breaks this down into two distinct, massive engineering costs: the developer tax and the operator tax.
Let's dig into the mechanics of those because I think a lot of our listeners will resonate with this. What does the developer tax actually look like for an engineer writing code day to day?
The developer tax is basically the daily friction application engineers face because their code is inextricably tied to the operational configuration of that centralized cloud.
So they can't just write code.
No, not at all. Instead of just writing a brilliant piece of business logic like a better recommendation algorithm, they have to write code that's deeply aware of exactly where it's going to run physically. They have to handle environment-specific behaviors, they have to hard-code region-specific endpoints, and they have to write incredibly complex retry logic in case one of those distant origin servers fails during that long network round trip we talked about.
Butcher's article actually says they're forced to become YAML experts. Now, for the listener who might not be deep in the DevOps trenches every day, what is YAML and why is it taxing developers so heavily?
YAML stands for YAML Ain't Markup Language. It's a recursive acronym. It's a human-readable data serialization format.
Human-readable, theoretically.
Theoretically, yes. In theory, it was meant to make configuration files easy to read. But in modern cloud infrastructure, it is mutated into an absolute nightmare.
How bad does it get?
You have thousands of lines of YAML dictating exactly how a container should behave, what memory it gets, what virtual network it talks to, what ports are open. Instead of being software engineers writing applications, they basically become configuration managers.
Just debugging text files.
Exactly. They spend hours debugging spacing errors in a text file. Because in YAML, if you miss one indentation, one single space in line 4000, the whole deployment can crash. Every time they want to test a simple logic change, they have to package it up, adjust the YAML, and send it on a round trip to a remote testing environment that mimics the bloated production setup.
That sounds exhausting.
It entirely destroys their flow state. It's a massive tax on their time and cognitive load.
So that's the developer tax. What about the operator tax? Because someone has to maintain all this infrastructure.
Right. The operator tax falls on the platform teams, the DevOps engineers, the SREs, the people responsible for keeping the whole apparatus running and available 24/7.
The ones carrying the pagers?
Exactly. Because the centralized architecture is so incredibly heavy and brittle, deploying updates is terrifying. They literally spend weeks planning multi-region rollouts just to ensure they don't break anything.
The blast radius is too big.
Yes. They have to constantly tune those inefficient autoscalers we just talked about. They're constantly patching container images for security vulnerabilities. And they're endlessly fighting something called configuration drift.
Configuration drift, what's that?
It's where a server in London somehow ends up with slightly different settings than a server in Tokyo.
Yeah.
Causing these random localized bugs that take days to track down. It's just endless, exhausting toil.
Okay, I see the pain there, but let me play devil's advocate for a second.
Go for it.
If I'm serving millions of users across 50 different countries, doesn't global scale inherently demand complex YAML and configuration files? I mean, isn't some of this just the unavoidable reality of modern software? Can we really avoid the operator tax when the stakes are that high?
That's the conventional wisdom, right? That scale equals complexity. And it's exactly the mindset that Bond and Butcher are challenging. And this is where Dieter Ram's philosophy provides the perfect counter-argument to that conventional wisdom. Ram said that good design is unobtrusive. It should recede into the background. Your tools should not demand your constant attention. They should simply empower you to do the actual work.
Like a good hammer doesn't make you think about the hammer.
Exactly. If your infrastructure demands that you spend 50% of your engineering time managing its configuration, the infrastructure itself is poorly designed. Period.
It's like having a high-end stereo where you have to unscrew the back panel and manually solder the frequency crystals every single time you want to change the radio station.
That is exactly what it's like. True scale shouldn't mean compounding complexity for the human operator. As we'll see in a minute when we discuss the edge computing solution, it is physically possible to have simple code deployment entirely replace multi-region operational burdens.
Right.
It's a matter of shifting the complexity away from the human and baking it into the network layer itself. And we really have to consider how this disproportionately impacts junior engineers.
That's a crucial point. We need to simplify the developer tax for junior engineers navigating complex cloud infrastructure setups. How does this bloated environment affect someone just starting out?
It's paralyzing. When you have a labyrinth of centralized cloud configurations, it literally takes months for a junior engineer to safely push a single line of code to production.
Because they don't understand the blast radius.
Right, they're terrified of breaking the brittle infrastructure because the blast radius is so large and the systems are so coupled together. It completely slows down onboarding, it kills innovation, and it turns what should be an exciting creative process into a bureaucratic exercise in risk management.
We need to simplify it so that new talent can actually navigate the infrastructure and build things rather than just untangling legacy YAML files.
Exactly. Minimal designs actively reduce developer tax and operational friction.
So we have the human cost of managing our internal code. But if I'm bolting together multiple different vendors to handle my global scale, my first thought is the complexity and the fees are going to multiply.
Which brings us to arguably the most dangerous friction point of all in this deep dive, the cost of architectural seams and vendor fragmentation.
This is such a critical concept in our source material, the cost of the seams.
Explain that for us.
Well, in the pursuit of optimization, companies often adopt a best-of-breed approach. They look at their architecture and they pick one vendor for their content delivery network, a completely different vendor for bot management.
Maybe a massive hyperscaler for their core compute.
Right, and maybe a specialized fourth vendor for AI inference.
And on a PowerPoint presentation for the board, that looks incredibly smart, right? You're using the absolute specialized, perfect tool for every specific job.
On paper, it looks beautifully modular and efficient. But in physical reality, an architecture that is fragmented across multiple single-purpose vendors is incredibly fragile and highly taxed.
The seams between them are the problem. Exactly. Every time a piece of data has to cross the boundary, the seam between one vendor and another, you incur a massive threefold penalty.
Let's break down this threefold penalty because this is where the invisible money drain really happens. What is the first hit?
The first is purely financial. Cross-vendor egress. Remember those egress fees we talked about earlier? The 9 to 12 cents a gigabyte?
How could I forget?
Well, the whole benefit of moving some logic away from your core origin evaporates if your edge vendor has to constantly call back to a completely different cloud provider's origin to fetch data. You're paying a toll at every single network hop between these different corporate entities.
Right. Every time vendor A talks to vendor B, someone is generating a bill. But it can't just be a financial hit. What happens to the latency when you have to cross the public internet between these vendor silos?
That's the second penalty, latency. Every time a request leaves one vendor's network to enter another's, it has to physically traverse the public internet. And when you're on the public internet, you're dealing with Border Gateway Protocol or BGP routing.
BGP routing. What does that mean exactly for the data?
It means your data isn't taking a straight line. It's hopping between different internet service providers, hitting unpredictable traffic jams, and moving at the pace of the slowest physical layer.
So it's taking the scenic route.
Yes. You might have built a personalization engine that processes data in 10 milliseconds. But if it takes 150 milliseconds for the request to physically hop across the internet from your CDN vendor to your compute vendor, your user still experiences a slow, sluggish application.
The performance just degrades exponentially with every seam you introduce into the architecture.
Exactly. And then what's the third penalty?
Let me guess. More human suffering.
You got it. Human capital. Engineering hours. Vendors do not natively talk to each other. To make vendor A's bot manager share threat intelligence with vendor C's database, your engineers have to build the bridges.
Oh, the custom integrations.
Yes. They're writing custom API gateways, they're setting up complex message queues, and building synchronization layers. The industry calls this integration glue.
Integration glue.
And here's the kicker. None of this glue adds value to the end user. It doesn't make the product better. It's pure operational overhead. And it takes thousands of expensive engineering hours to build and maintain.
It's like buying the best engine from Germany, the best transmission from Japan, and the best chassis from America, and then wondering why it takes your mechanic 6 months and $1 million to make the car actually drive.
That is a brilliant way to look at it.
So what we've built is an architecture that bleeds money in egress tolls, wastes money on idle server capacity, burns out engineers with configuration taxes, and slows down users because of fragmented vendor seams. It is the ultimate anti-Dieter Rams design. It's cluttered, it's inefficient, and it's functionally chaotic.
which means the only way out is to apply true first principles thinking. To eliminate the cost of these seams, we have to look to a unified, minimalist solution. We have to bring the logic as close to the user as physically possible, and we have to do it on a single, continuous network.
And that is where the narrative shifts. Because we're moving from the diagnosis of the trillion-dollar blind spot to the less but better solution, lean edge efficiency. Let's talk about edge computing.
Yes, the antidote.
Specifically, how the Akamai source presents it as the minimalist antidote to this massive centralized cloud bloat. Detail how edge computing simplifies complex cloud architectures to reduce latency and egress fees for us.
To understand the solution, we have to completely rethink where code physically executes. Instead of forcing every single user request to travel all the way back to a centralized server farm, edge computing distributes the compute power across thousands of nodes globally.
So it's decentralized.
Highly decentralized. It places the brain of the operation right at the internet's front door.
Yeah.
Going back to your postal analogy from earlier, it's putting the smart mail carrier on every street corner.
And the Akamai piece highlights their specific implementation of this. Akamai functions running alongside edge workers. What this allows you to do is take all those high-frequency, lightweight tasks we talked about earlier.
Right, the personalization, token validation, mass redirects, and bot misdirection.
Exactly. And you run that logic directly on the edge network itself.
Yes. But to really appreciate it, we need to look at how the underlying mechanics of edge computing actually solve the specific bottlenecks we just spent the first half of the deep dive exploring.
Let's do it. Let's start with the idle capacity problem, the empty apartments. How does this lean edge efficiency solve that?
It solves it through a fundamentally different compute architecture. Akamai functions are designed with sub-millisecond cold starts.
Sub-millisecond. Like
Yeah.
a fraction of a single millisecond. How is that even physically possible when we just established that centralized clouds take minutes to boot up an operating system in a container?
Because edge functions don't boot an operating system or a heavy container.
What do they use instead?
They use technologies like V8 isolates or WebAssembly. Instead of spinning up a whole virtual machine for every task, the edge node already has a highly optimized runtime engine humming along constantly. When a request comes in, it simply spins up a tiny isolated sandbox for your specific code, executes it, and tears it down immediately.
So there's no booting Linux, no connecting heavy resources.
Right, because the startup time is practically zero, you don't need a minimum instance floor. You don't need to keep servers warm just in case. The compute scales instantaneously with demand, meaning you only pay for the exact milliseconds your code is actively running.
Wow.
The cost of idle capacity is entirely eliminated. This is the ultimate execution of RAM's visual order and reduction. You've removed the bloated, unused parts of the system entirely.
Okay, that covers the idle waste. What about the compounding egress fees? The tolls on the highway?
They evaporate.
Evaporate. How?
Here's the mechanism why. The logic runs, and the decision is made before a single byte of egress is ever billed at the origin. If a malicious bot tries to access your site, the edge node identifies it and drops the connection right there at the front door.
Oh, I see. The origin server never even knows it happened.
Exactly. Therefore, there's no round trip and no egress fee. You're applying first principles thinking.
Huh.
The absolute best way to reduce the cost of moving data is to simply not move the data.
That is incredibly elegant, but let me push back again, specifically on security this time.
Sure.
If I'm taking my core business logic, my authentication, my user routing, and I'm spreading it across 4,400 points of presence globally instead of keeping it locked down in a fortified fortress in Virginia, aren't I just creating a massive attack surface? Doesn't edge computing make security a nightmare?
That's a very intuitive concern, but it actually works in reverse.
How so?
By moving the logic to the edge, you're building a perimeter defense. Think about it. In a centralized model, traffic, including malicious traffic, like a DDoS attack, has to reach your origin before you can evaluate it and drop it. You're letting the attackers all the way to your castle gates before you even start checking their IDs.
Right, they're already at the door.
With edge computing, you're checking IDs at the outer borders of your empire. You're absorbing massive DDoS attacks and filtering SQL injections thousands of miles away from your database. It drastically reduces the attack surface of your actual origin.
I really hadn't thought about it like that. Okay, what about the operator tags? We discussed how painful multi-region deployments are with all the YAML files. Explain how simple code deployment replaces complex multi-region operational burdens. How does the edge actually simplify that?
Because the edge network operates as a single, unified, global fabric. When an engineer wants to deploy an Akamai function, they don't have to write a YAML file for the Tokyo region. and a different one for the Frankfurt region, and then coordinate a highly stressful phase rollout.
What do they do?
They run a single command, and the network automatically distributes that code to all those thousands of points of presence globally in seconds. The infrastructure recedes into the background. The developer simply writes code, and the network handles the global distribution instantly.
That directly answers the friction junior engineers face. They don't need to be YAML experts. They just need to write good code. And this ties directly into Prasad Bond's concept of parameter engineering, doesn't it?
It absolutely does.
Yeah.
Bond demands that we impose severe boundary conditions on our builds. He says, force scripts to execute in under 200 milliseconds.
Which is incredibly fast.
It is, but when you eliminate the massive latency of the network round trip, your code actually can execute in those incredibly tight timeframes. By removing the friction points, you aren't just saving money. You're fundamentally changing the speed at which a company can innovate. Engineers can test, deploy, and iterate in minutes instead of weeks.
But there's one final piece to this puzzle. The seams. The vendor fragmentation. If I use an edge provider for my compute, but a different vendor for my CDN and a different one for security, aren't I just moving the seams to the edge?
That is the brilliant part of a truly unified edge architecture like Akamai's. Akamai functions run on the exact same network as Akamai's CDN, their cloud compute, and their security stack, like Bot Manager.
Ah, so they share the exact same physical infrastructure.
Yes. This is exactly how you eliminate the cost of the seams. A single user request hits the front door. The Akamai Bot Manager classifies it immediately. It hands it off to an Akamai function to rewrite the URL or validate an auth token. If it needs core compute, it fetches it from Akamai Cloud Storage.
All in the same place.
And if it needs AI, it calls inference on local GPUs. All of this happens seamlessly, instantly, without the request ever leaving the Akamai network. There is no cross-vendor egress fee. There's no latency penalty for hopping across the public internet. And there are no engineering hours wasted building integration glue.
It's the complete realization of less but better. You've taken a fragmented, complex, highly taxed architecture and reduced it to a single, unified flow. Minimal designs actively reduce the developer tax.
And to truly understand the magnitude of this architectural shift, we need to look at exactly how this transforms the bottom line for modern business. We need to move from theory to physical reality.
Right, because Bond explicitly warns against abstract business theories. He demands raw data and physical component efficiency. So let's look at the real-world e-commerce example outlined in the Akamai source. This is the proof of restorative engineering in action.
Let's walk through it.
Let's walk through the old way first. What does this medium-sized e-commerce company look like before they adopt a lean-edge architecture?
In the old way, their architecture is a classic fragmented stack. A user logs in, and the traffic hits a separate bot management vendor sitting in front of a CDN. The CDN sits in front of a hyperscaler cloud region, acting as the origin.
Okay, so that's 3 hops already.
And that origin server frequently has to call out to a completely separate third-party AI platform to generate product recommendations for the shoppers.
So data is literally ping-ponging across 4 different corporate entities just to load a storefront?
Precisely. So what's the result? Every single page load fires this entire chain. Each request pays egress to ship the personalized payload back across the network. For a medium e-commerce site, the source notes this egress alone is a 6-figure annual expense.
Hundreds of thousands of dollars just on transit.
Yes. And when a flash sale happens, there are centralized cluster spikes, but they're paying permanent scaling costs just to maintain the readiness for those temporary spikes. And their platform team is spending weeks every single quarter just trying to coordinate deployments across these 4 different vendors.
And what is the latency on all that ping-ponging?
Because the recommendations have to cross 3 different networks per request, from the CDN to the origin to the inference vendor, and all the way back, the latency is hovering around 200 milliseconds.
Okay, 200 milliseconds doesn't sound like a lot to a human, but in digital commerce, that's an absolute eternity. Amazon proved years ago that every 100 milliseconds of latency costs them 1% in sales. It's cart abandonment territory.
Exactly. It directly impacts revenue.
So they bring in the quiet architect, they apply Dieter Ram's design philosophy, they shift to the new edge way. What happens to the exact same e-commerce workload?
The transformation is immediate and highly measurable. First, the logic for personalization, authentication, and redirects is moved out of the origin and pushed to the edge via Akamai functions.
Okay.
Because the decision is made right next to the user, the round-trip latency drops from 200 milliseconds down to 40 milliseconds.
So that's a massive performance upgrade. That's a huge win for the user experience.
It is. Next, the bot manager is integrated natively at the edge. Suspect traffic is rewritten or blocked before the origin server ever even sees it. This instantly drops the load on the origin, saving massive compute costs.
Because you aren't processing junk traffic.
Exactly. Then, instead of calling out to a third party for product recommendations, the AI recommendations are run on the NVIDIA AI grid directly at the edge.
Wait, they run the AI inference at the edge too. I always thought AI required massive centralized server farms.
Training an AI model requires massive server farms, yes. But inference, which is simply taking a user's data and running it through the already trained model to get a recommendation that can absolutely be done at the edge.
Oh, that makes sense.
And because it's running on-edge GPUs on the same network, the AI inference costs fall by up to 86%.
86%. Just because they aren't paying the toll booths to transport the data back and forth to an external AI vendor, breaking down how eliminating cross-vendor egress fees boosts bottom-line profit margins is just, it's astonishing.
Yes, the six-figure egress fees simply evaporate because there is no cross-vendor transit. The data never leaves the unified network.
And for the engineers?
The operator tax is completely gone.
Yeah.
No per-region rollouts, no massive YAML files to sync across vendors, no integration glue. Deployment is handled with a single command. Quantifying how removing vendor seams directly increases annual enterprise profit margins, it's huge.
By simply moving the brain of the operation to the front door, you aren't just saving milliseconds. You're saving millions of dollars in egress and compute. And maybe more importantly, you're saving your engineering team's sanity.
You're restoring their capability.
You're restoring their capability to actually build things rather than just act as highly paid plumbers fixing leaks in a bloated system.
It's the perfect synthesis of our sources. You've identified the trillion-dollar blind spot, you've applied the rigorous first principles of restorative engineering, and you've utilized the lean efficiency of the edge to create an architecture that is functionally clear, visually ordered, and radically reduced.
It's honest design for the digital age. Contrast centralized cloud bloat with lean edge efficiency, and the winner is obvious.
It really is.
Okay, let's take a breath and recap the journey we just went on because we covered a massive amount of ground today. We started by looking at the executive dashboards and how they hide the trillion-dollar blind spot of centralized cloud architecture, celebrating 15% savings while totally ignoring structural rot.
We exposed the punishing physics of the origin server trap, where compounding egress fees act like literal toll booths for every piece of data making that long round trip.
We busted the myth of elasticity, revealing that up to 65% of paid cloud capacity is just sitting idle empty apartments burning capital because standard virtual machines are too slow to boot up during a traffic spike.
We detailed the human cost, showing how complex YAML configurations and fragmented vendor seams create a massive tax on developers and operators, especially junior engineers who get completely bogged down in configuration rather than creation.
And finally, we discovered the solution. By applying Dieter Rams's less but better philosophy, we saw how minimalist edge computing, specifically solutions like Akamai functions running on a unified network, can eradicate egress fees, slash latency from 200 down to 40 milliseconds, and restore efficiency and dignity to the engineering process.
As we wrap up, I really want to leave the listener with a final thought to ponder. There's a famous concept in software engineering called Conway's Law.
Conway's Law, let's hear it.
It states that organizations inevitably design systems that mirror their own internal communication structures.
Oh, that's fascinating. So a siloed bureaucratic company naturally builds siloed bureaucratic software.
Exactly. If a company is highly fragmented across departments, their cloud architecture will be fragmented across vendors. But here's the provocative question. Does Conway's Law work in reverse?
In reverse.
Yes. If an organization makes the conscious, difficult choice to tear down their bloated, highly taxed cloud architecture, and they adopt a lean, unified, and minimalist edge architecture, will the company culture itself eventually become less bureaucratic, less siloed, and radically more innovative?
Wow. If you strip the unnecessary buttons off the radio, do the people listening to it become more focused? That is a brilliant thought to leave on. Thank you for joining us on this dive. I encourage you to go back to your desk today, pull up your architecture diagrams, and look at your own digital infrastructure through the lens of a quiet architect. Ask yourself, where are the seams? Where are the empty apartments? And what can you strip away to make it simply better?